So more programming. I managed to figure out this. I'd been stuck on exercise 1.6 in the last video, but I wound up figuring it out in email. And basically just summing up, because I wrote a fair amount, but summing up very briefly, the issue with 1.6 was that stuff, if is a special form, and that affects how stuff gets evaluated. But if you try and define your own if, it's not going to be a special form. And so it's going to apply the normal evaluation rules, the applicative order evaluation. And when it does that, this is going to lead to an infinite regress. And I explain that in detail in my post yesterday, September 16th. And I found like some discussion online, and my answer seemed to be the same as other people's, so that's good. So let's see, 1.7. The good enough test, which is, I have two of these open. I guess I'll close the one with the version with new if, because I don't want that. Okay. So the good enough test is used in computing square roots will not be very effective for finding the square roots of very small numbers. And oops. Right, so the good enough test used in computing square roots will not be very effective for finding the square roots of very small numbers. Why? Well, because the way it's detecting whether it's figuring out something is good enough is, okay, it takes a guess and the number whose square root you're trying to find, and it says, okay, is the difference between the square of your guess and the number whose square root you're trying to find less than 1,000. And that's a fine threshold for, like, normal numbers you might encounter, in many situations, but it's not like fine enough to catch like really small numbers. So like I did like square root of whatever this is, and the actual value is this, but the value it spit out was this, and you can see this is 300ths, and this is 300,000, 10,000, 100,000, 3 millionths. So that's a big error, right? Where's my recording monitor? Okay. I'm going to pause this actually. Okay, so that's why it's not going to work for small numbers. Also, in real computers, arithmetic operations are almost always performed with limited precision. This makes our test inadequate for very large numbers. Okay, so I tried finding the square root of various numbers, and I kept adding 3 zeros to the end until I got to square root of 1 with 15 zeros. And this is where it started looping. And so it starts out fine, but then it gets to a point where it's not really, it's like it's not getting any closer. And so I think what's happening is because there's only so much accuracy, Like it only is keeping track of like 16 or 17 digits or something like that from what I counted. And since good enough is based on having like finding the difference in the value of the number you're looking for and the square of the guessed and seeing if it's within 1/1000th. And so what was happening is that the square of the guess, because scheme was only keeping track of so many digits, the square was hitting, like it wasn't coming within more than 1/10, and that 1/10 is what's being like if it's never coming, like this was not coming more than within 1/10 of this, the initial value that you look for. And since our threshold is not 1/10 but 1/1000th, it never comes within the threshold. It never closes the deal. So, right. So this makes our test inadequate for very large numbers. Explain these statements with examples showing how the test fails for small and large numbers. Yeah, I mean, I've already been through that. An alternative strategy for implementing good enough is to watch how guess changes from one iteration to the next and stop when the change is a very small fraction of the guess. Interesting. Design a square root procedure that uses this kind of end test. Alright, so I got a little stuck here. I think I was overcomplicating this. But it's actually pretty simple. One misconception that I had was that I really had to take a step back and be like, okay, well, if they're asking for an alternative strategy for implementing good enough, and we're this early in the text, I mean, I know this was like for MIT students, but it can't be that complicated. So I was like, well, am I going to have to like keep track of the improved guess and the like old guess and new guess or something? And then I was like, no, because I sort of gave the answer in a misstatement of what I was thinking, because we already have improved guess, which runs a thing to improve the guess. So if we want to do something that's about the relationship, like we want to see what the relationship is between like the current guess and the improved guess, and judge like the amount of difference, then we can do that just by calling on improve and giving a guess and the number that we're looking for, and then that essentially keeps track of, like, that's what, it's not really keeping track, but that gives us the value that we need to compare. So like, you call square root iter and the guess, and then it sees if it's good enough, and within the good enough, you're giving it like, guess level 1, okay? Stage 1, phase 1, first guess. Maybe just call it, the first guess. And then, so mathematically, actually, I'll just finish the thought. So you give it the first guess, and then you can call improved guess within good enough, and then you can compare the two values. You've got guess, and you've got the improved guess. So you've got the first guess and then the second guess. and you can deal with those. And right, and so mathematically, like what I think you want to do is you want to figure out the improved guess. So yeah, so I did improved guess minus guess divided by the guess, and then is the absolute value of that whole thing less than 1,000. And why did I do it this way? Well, so I think, yeah, if you're going to like the first part, because what you really want is like the amount of change in the guess, and you could actually, so for like the numerator, like it, like if I don't know, if the first guess was like, say, I'm just making up numbers here, but the first guess was say 5, and then the improved guess was 4, and then you say, you know, guess minus improved guess, which is different than how I did it here, then you'd get 5 minus 4 equals 1. But then if you did it the other way, like you did 4 minus 5, you get -1. But in both cases, the denominator would be that first guess, so that would be the same. And then I have the absolute value thing, so I think it's all good. It all works out. So yeah, I don't think the like I had some doubt. I'm saying this out loud because I'm like I had some doubt. Like, is it that like sensitive to the order of the wood? But I think I handled that, the absolute value thing. And then I just like sort of imported the zeros because 001 thousandth was in the other thing. So I just like it was serving a different function, but I was just like, well, that seems like, you know, or watch how guess changes from one iteration to the next and stop when the change is a very small fraction of the guess. So this would basically terminate when the improved guess is a tiny right. So like if say the first guess was 1,000, I'll make the numbers really easy on myself, you know. So if the first guess was 1,000, then for this to come out as being good enough, the improved guess would have to be either, it would have to be within, the second guess would have to be like greater than 999 or less than 1,001. It would have to be within 1. So the change is pretty tiny at that point. So that seemed fine to me. So I think earlier in the video I'd done like, taking the square root of this number, and you see what it gives you here. With this is the old procedure. This is the initial version. And you see the big difference between that and Google, right? A lot of decimal places there. But then, if you right. So if you run this number, I don't even want to count. I just like pasted 1 zillionth, square root of a zillionth. And right, this looks a little weird, but I'm pretty sure this is like, you know, it's just like scientific notation for the tiny numbers. So this means like you shift the decimal 6 places to the left, which if we were starting here, it'd be 1, 2, 3, 4, 5, 6. And then, so that's the right place. And then you see it's 3, 1, 6, 2, 2, and this is 7, and this is 8. So it's not super exact, but it's way closer than like, what it was before, whatever that was. And it was like, it was bad. Oh, I guess I have it here. Yeah, 300ths. Yeah. So that's much better. And then, so let's do the old one again. So I'm going to have to stop this one because it doesn't terminate. It keeps going, going, going. Right, okay, so that's cool. I should have pasted this first, lol. Okay. And we grab that. And then put that in here. And you get a number. And the number that you get, yeah, 1, 2, 3, 4, 5. Right, 1, 2, 3. Yeah, it's the right digits. It's, it's in the ballpark. So, pretty good. All right. Exercise 1.8. Newton's methods for cube roots, or Newton's method for cube roots is based on the fact that if y is an approximation to the cube root of x, then, okay, I'm already getting lost. Okay, is based on the fact that if y is an approximation to the cube root of x, then a better approximation is given by the value, this thing, which is barely readable, although it is readable. All right, so basically what I did as my answer attempt is I started out with where I was in exercise 1.7, and then I commented out average, and I basically put this into the improve, and I put yes instead of y. But otherwise it's the same. And then I changed like the name to cube root and cube iter. That's pretty much all I did. And it seemed to work okay, and I tried some normal values like 64 and that sort of thing. And I tried some bigger values, some like extreme values, like similar to what I tried before. Like, what did I do? I did like 1 and 15 digits, and then it took a while because I've got all this trace stuff showing the steps. It took a while, but where is it? There we go. Should make this a little bigger. Yeah, so it got there, approximately. And then this tiny number, did the cube root of that. And I got that, and I checked it in the Google, and that came out okay. So that actually seemed pretty straightforward. Initially, so like pause the video while I was thinking, and then I started doing some stuff, and I didn't start it up again. But initially, I was like trying to do this part, and good enough for some reason. I think I maybe like I need to keep track of what the role of the different parts is better. I mean, like they're labeled, right? But like you just, you have to think about it some because like if you do keep track of that, you introduce unnecessary complications. Like they're actually trying to break it down here and keep what you have to do fairly discreet. You know, because you're changing the improve. Like you see, I commented out the average stuff because like we didn't need that. Um, but they're trying to keep the part that you actually have to change like fairly discreet and easy at this stage. So you want to make sure you get the right part, or else you just make it unnecessarily hard on yourself. Okay. Maybe I'll just. I think these are okay, but I think it'll be good to see if I can find some answers online and compare. All right, so I found this page with a bunch of. It's like some sort of wiki where people have contributed different answers, which is cool because it's good to get different perspectives on how to solve the problem. And if there's like 5 answers, it's more likely that you'll see one that is yours or is maybe at least kind of close to yours. So let's see. An alternative. I guess this is one way to actually which goes with which. Okay. I think, yeah. So, one way to watch how guess changes from one iteration to the next, yada yada, is to see it as a rate of change using classic x1 minus xo divided by xo. Yeah, this is, I mean, I learned this in like school. I think like this was like some, and also I think I went over it in that pre-algebra book, Art of Problem Solving. I think they talked about that. Um, in this case, x1 equals improved guess and xo equals guess. This is equivalent to the first solution, but is more explicit about calculating the rate of change. So, actually, yeah, this one is. I'll adjust the spacing so it's more schemy, and then, yeah, no, that's cool. But it's exactly on point. That's always good. So, because it's not like I tested it super well. So I mean I tested a few cases, but it's good to see somebody else had the same idea. You know, this is one of the things that people like about uh, university coursework or whatever is there's like a bunch of people who are all working on the same set of stuff and talking about them. But like you could do that so much better online. But like you have to do it. Like there has to be stuff that exists where people can have discussions about things on an ongoing basis. Like there has to be a culture of it. Like it there is some advantage to having a bunch of people working on the same thing, and like how it can be, if you have a ton of people uh, working together on problems, and you can find people who, you know, you like to have a study group or whatever. But you could do similar things online, but we don't really have as much of a culture of doing that. So anyway, total tangent. Read through some of these other ones. Alternative approaches stop iteration when the error was less than a given proportion of x. So what is this? This is interesting. Rather than comparing like the ratio of the change in the guesses, this guy is just like squaring the guess and seeing if it's within a certain range of the original number whose square you're trying to estimate. Oh, this might be better actually. So this guy, George W. Bush, says, I think the hint is in the question. In real computers, arithmetic operations are almost always performed with limited precision. Given that it's done with limited precision, at some point, improved doesn't actually change the guess anymore. This is my solution. And so it's like if the improved guess, if, the change in the, well, okay, let me start again. He's saying it's good enough, the guess is good enough if the guess and the improved guess are the same. So putting it in terms of what I was doing earlier, if like the amount of change between improved guess and guess is 0, then this guy then that's what this definition of good enough is. My only concern would be that it would take a while. So that's an issue. And then he gets some criticism. This guy says if the answer is in the form of some repeating fractional number, the equal comparison will never succeed. And then somebody replies that they disagree with this. And when improved guess x hits the machine's precision, it will yield the same guess it got as input. Right, so you're basically going up to the machine's precision limit, which again, like I said, I'd be concerned about maybe taking too long, but yeah, I don't see why it wouldn't work. This is cool. I think I'll call it a video here and check my 1.8 answer, maybe starting the next vid.